Hello, this is lesson 5.1 talking about bisectors of triangles. So we're going to identify and use perpendicular bisectors, and then we're going to identify and use angle bisectors. So let's go ahead and start with a perpendicular bisector. So here we have this being bisected and it's perpendicular. So CD bisecting AB. And so that would make AC equal to BC. So where are those pieces here? So if these down here are being bisected, which we have our tick marks, then this segment is congruent to this segment. So we're going to put CB right there, or BC. All right, the next one then is the converse, going the other direction. So if we know that this is being bisected perpendicular, and we know this segment is congruent to this segment, then we know that this point E lies on CD, the actual perpendicular bisector, the perpendicular bisector of AB. So it actually is bisecting AB is what we're saying here. If we know this segment and this segment are congruent, and it's going straight through this point here on the triangle. So that's the converse because we're going the other direction. So this stating the segments are congruent, this one we know that this line is the perpendicular bisector. So here's some vocab I want you to kind of refresh your brain with. You know perpendicular bisector, you've seen it before. What's equidistant from 2 points? You could probably write that out yourself. Distant from a point to a line, kind of talked a little bit about that above. Concurrent lines, so that's one that's new here, where it's 3 or more lines that are intersecting at a common point, and we're going to have 4 different types we're going to look at in the next 2 lessons. And that point of concurrency is where the 3 lines meet. So the lines are concurrent, the point of concurrency is going to have its own specific name for each of the 4 that we're going to talk about. So let's just kind of talk about perpendicular bisector and kind of what that does to these triangles. And then we're going to look at it within kind of a couple of different triangles. So the segment length in the diagram here that are equal, well, that would definitely be the ones that we can see here with tick marks. So CQ is going to be congruent to DQ. And then we also can state then if those are congruent, we can see, well, this is 7 and this is 7. So those are going to be congruent. So that's going to be CT is congruent to DT. All right, and then we also have that CP is going to be congruent to DP because this triangle here, if those are congruent, and this is a perpendicular bisector, they meet here at P, then this one is going to be congruent to this one. So CP is congruent to DP. All right, so explain why T is on PQ. Well, because we know that both of these are congruent and both of these are congruent, and this is a perpendicular bisector and it goes through that point, the converse, and you can look back at that, of the perpendicular bisector theorem explains why T is on that line. All right, so down here a couple of examples. We know that these are congruent and this is perpendicular, so that means that this segment AC is congruent to BC, so that would make it 8.5 by the perpendicular bisector theorem. Over here we know the sides are congruent by those tick marks, and then we know this is perpendicular through W, so what is this distance? Well, if this is 6, then that also has to be 6 by the converse, because we already have those sides. And then the last one is, we know that these are congruent, and this is a perpendicular bisector, so then PQ is congruent to RQ. So we're going to set those equal and solve, and then we do need to plug it back in because it's asking for PQ and not X. So let's subtract 3X from both sides. 1 is equal to 2X minus 3. If we add 3, Then 4 is equal to 2x. Divide both sides by 2. X is 2, which means when we plug it back in, 3 times 2 plus 1 to find PQ, it's 7. And that again is the perpendicular bisector theorem. So when we have a perpendicular bisector point of intersection forms what's called the circumcenter. So I always think of this as the center of our circle. And this circle can be drawn on the outside, which we'll see here in just a second. But it is formed by taking and doing the bisector of each side and making it perpendicular. And then we meet at what's called the circumcenter, which is the point equidistant from the vertices of the triangle. So here is an example, and this shows like from this point to here, from this vertex to here, from this vertex to here. These are all the same distance. Okay, so if we have the acute triangle, it's too small, you can't really see it written. We have obtuse, but it's kind of small. Then we're in the inside. If we have the obtuse, you can't read it, but we'll make it, then we are on the outside, outside obtuse. If we are a right triangle, then we are on. So these are where our circumcenters are meeting. So we have kind of 3 types there. So some key things about circumcenter. Circumcenter, I always think of, okay, back to my my kind of FBI or, police shows. We have, the incidences that occurred here, here, and here. Where are they going to strike next? So we kind of draw, our circle and figure out, well, they're probably going to be, somewhere in the middle. So the point equidistant from all of those other incidences or vertex points is your circumcenter. So let's go to the circumcenter to see where the next crime is going to happen. So I watch too much of those kind of shows. So here we have that these are going to be all the same distance from our incidences, as I'm calling them. So what would be BD? Well, it's going to be the same distance. If we know from A to D is 11.5, then B to D is 11.5. So this is the same as this. And then it's also going to be DC. It's the same distance from that. Or maybe where does that person, the perp, live? They live in the middle. You could think of it like that. So 3 people need to, this one's a happier example, they need to decide on a location to hold the meeting. So they will all be coming from different places in the city. They want to make the meeting location the same distance. So why is the circumcenter the best place to meet? Well, why is it the fairest? Because it's equidistant from all 3 points or people. So they all only have to travel the same distance to meet, which is only fair. All right, so the other thing, besides this being the same as this and this, we also know that these are called perpendicular bisectors. So here's the perpendicular, here's the bisecting. So I should make those 2. And then here on this side is the bisecting. And then here over here is the bisecting. So what is congruent to VW? Well, VW is that distance here, so it's going to be congruent to this distance here of XW. What's going to be congruent to our AZ? Well, this distance here of AV. And then what's going to be congruent over here to XY? Well, ZY. And then talking about our green here, these are our 3 different points from XU to, and VU, what is it also congruent to? ZU. Okay, so that is talking about circumcenter. So now we're going to change our tune here and talk about angle bisectors and kind of what that lends itself to for our next kind of triangle. So it is equidistant from the sides of the angle. So if a point on the is on the bisector of an angle, then it is equidistant from the sides. So this is congruent to that. All right, next, so DF is going to be congruent to FE. It is on the bisector of the angle is what's written right here. So the converse is also true. If a point in the interior of the angle is equidistant from the sides, so we know that these are equidistant, then it is on the bisector of the angle. Okay, so that means that BF is going to bisect angle DBE. So what that means for this example here is if R is on the bisector of this, and we know that this is perpendicular, these angles here are being bisected, then this segment is congruent to this segment by the angle bisector theorem. Those segments are congruent. So let's practice a couple of examples using those 2 pieces of information. So BD, we want to figure out what that is, or DB, and we know that this is 5. We know that this is being bisected, and we know these are perpendicular, so this distance and this distance would be the same by the angle bisector theorem, which would make it 5. So this angle here is 28. We want to figure out what that angle is, and we do know that this is congruent to this, and it's perpendicular, so that means that this is on the bisector. So if that's 28, the angle next to it has to be 28 because it's being bisected, so that would make them equal. Again, here being this is the converse of the angle bisector theorem. This here would make these equal because it's the angle bisector and these are perpendicular, then this would be congruent to this. So we're going to set that up and solve. So you should get x is 3, and then when we plug 3 back in up here, we get QS is 11. Go ahead and read through some of this vocab. Much of it you already know, but in-center is our new word where they are equidistant when it is an angle bisector. So that's what we're going to look at next. So angle bisector, it's called the in-center where they meet, and it's equidistance from the sides of the triangle. So I think in the center of the circle that's inside, so we have another kind of circle. These are the radiuses, which make them all the same. So PT is equal to PU, which is equal to PV. And we're going to find PT. Well, PT here, we have to figure out what that is, but we know 2 sides of this triangle, which is a right triangle, so we can use Pythagorean theorem. So I'm going to jump over here and do Pythagorean theorem, where this is my A, this is my B, this is my C, and it's A squared plus B squared equals C squared. So plugging in my pieces, PT is A, 12 is B, C is 13, squaring the 12 and the 13, PT squared comes down. We subtract the 144 to get 25, and then we do the square root to get PT is 5. So if this is 5, that means that these are also 5 because they're the radius. Anything from the center to the outside of the circle is going to be the same. So the key pieces for in-center is that these are all the same, because they're all going to the outside and you can form that circle. The other piece is that this bisects. So these angles here are congruent to the one next to it. So to find SU, you need to use Pythagorean theorem again. You have A, B, C, so go ahead and use Pythagorean theorem and check. And you should have gotten 6. Try the rest and check. All right, take a look at the bottom and then check your answers. All right, double check your answers. Let me know if you have any questions.